Welcome, everybody, and thank you for joining us for the second webinar in the 2022 EnSafe Client Education Series. My name is Rich Heinzenberger. I'm a project manager here at EnSafe, and today's topic is layers of protection analysis as it relates to PSM, and it is being presented by Frank Rooney. Frank is a senior health and safety project director here at EnSafe, works out of the Jacksonville, Florida office. Again, thank you for joining us, and with no further ado, I'll turn it over to you, Frank. Take it away.
Thank you, Rich. Appreciate that. As Rich had mentioned, we are going to talk about layers of protection analysis as it relates to process safety management. Layers of protection analysis is something that you can use in a variety of different ways. But we have a lot of experience with it as a tool for PHAs, process hazard analyses. I'm going to take you through a little bit of what we've learned and how we kind of apply that in certain situations. There's a little bit about me. I've been around the business for quite some time. Been in EnSafe about 8 years now, and I am the EnSafe PSM Process Safety Management Service Lead. So if you had any questions about PSM, feel free to contact me. And enough about me, and on to the good stuff here. What is LOPA? Well, LOPA stands for Layers of Protection Analysis. And as the definition on the right states, it is a semi-quantitative method used to evaluate the frequency of potential incidents and the probability of failure of the protection layers. It's really a way to, and the way I use it, is a way to validate some of the qualitative judgments that folks use during a process hazard analysis. If any of you have ever been in a PHA before, you know that it's usually a group of people with extensive knowledge and experience sitting around the table and talking about the severity and the likelihood of certain outcomes from various processes. And a lot of times it's a qualitative judgment. Well, LOPA adds a little bit more quantification to that kind of judgment, and it's a way to really look at what are the safeguards you have in place and how reliable are they. And I'll get into some of the details around that in a minute, but that's really what the focus of LOPA is. And we're going to focus a lot on independent protection layers, and we'll talk about that, and trying to identify what the independent protection layers are, and do they relate to the Center for Chemical Process Safety criteria. And the Center CCPS is a subgroup of the American Institute of Chemical Engineering, and they have a lot of information on LOPA, and that's where they've used it in the past on trying to assess the reliability of these independent protection layers associated with chemical processes. A little bit more about LOPA. It's really an engineering tool used to assess the process risk and whether that risk has been reduced to an acceptable level. And we'll talk a little bit more about what the acceptable levels are. It's really, quite honestly, a judgment based on the client as to what they deem as acceptable, but we'll talk about how that is determined. And it's a methodology. It's a semi-quantitative means by which to validate, if you will, the qualitative judgments used in the PHA. And it's using specific criteria and restrictions for the evaluation of those IPLs, safeguards, if you will, to make sure that what you think is actually working behind the scenes to protect your process is actually there, and the failure rates and everything have been accounted for. What I want to make sure, though, is that LOPA is not regulatory driven. You won't find the phrase LOPA or layer of protection analysis anywhere in the OSHA PSM standard or in the EPA risk management plan regulation. It is really a best practice, and is really driven from a lot of companies trying to go above and beyond what a PHA may entail. Again, with the PSM standard and the risk management plan out there since the early 90s, many times we've gone through multiple iterations now of PHAs. And if you revalidate a PHA where the process hasn't changed much, it gets kind of rote. And folks said, oh, it hasn't changed much in 5 years, so therefore we're not going to really look at it closely, and it becomes more of a paperwork exercise than maybe an actual risk assessment. By adding LOPA to that PHA, I think it'll add some additional insight into some of the controls that you may have in place, some of the assumptions you may have been relying on for years, may be tested, and it's a great way to get a fresh look at maybe a process that has been around a long time and that people are getting kind of complacent about. When do we want to use LOPA? Typically applied after, as I said, a qualitative hazard analysis such as a HAZOP, and we're looking at the list of deviations and consequences related to potentially hazardous scenarios, essentially a PHA. It's usually used only to evaluate the most serious risks. You can do a LOPA on a variety of different things, but quite honestly, it does take a little bit of time. And so most clients like to focus on those, either the major or severe risks that are encountered, or areas where the residual risk tends to remain high. Maybe it's where the outcome could be a significant event, such as a catastrophic loss or a multiple fatality event. Or it could be where you rely heavily on administrative and personal protective equipment and SOPs as your main means of control, and you're a little nervous about doing that. Well, LOPA can kind of back up some of that nervousness, some of that qualitative judgment you may have used, and say that whether or not your layers are adequate to get you to the risk levels you think is appropriate. And if rule of thumb, it's typically applied to about 5% of the qualitatively identified risk. So if you're in a large PHA and you're looking at, hundreds of deviations, it'd be about 5% of those deviations that may necessitate a LOPA evaluation. So it's not used across everyone, but again, it really is going to depend on the profile of your process, how severe the outcomes would be, and maybe how much residual risk you have in your process. I'm going to take a pause here because I think this is a good time to talk about our first question, and that is, have you ever used layers of protection analysis? Let me go through a little example here because I tend to like examples, and I'm going to refer to this one a few times during the presentation, so hopefully this will sit well with you folks. Let's look at a typical PHA type of deviation. Here we have a flammable liquid storage tank. Let's say a flammable liquid of concern is acetone. And this is for better word, day tank. Say it's, maybe holds 500 pounds of acetone. And every shift, the operator opens a valve, flows in, I don't know, say 400 pounds of acetone, and hits the valve and closes it off. And then over the course of that shift, that acetone is used up. And every shift, that same process is repeated. The operator opens the valve and fills the tank, and then shuts the valve off, and they use it for other things. So our deviation, typically in a situation like that, would be overfilling that tank, leading to a fire. Obviously, acetone pretty flammable. And what the first deviation would be, well, what if we overfill that tank accidentally, resulting in a release, which then catches fire? And, in our qualitative judgment of severity, which usually most people tend to agree on, they would say, oh, that's probably a severity of 4 out of a 4 scale. Obviously, a fire with acetone, not something you desire, something that is something you want to avoid. And so we're going to give that the highest severity rating. And then we sit around the table and we go, okay, what kind of safeguards do we have in place? Well, first one is we have a standard operating procedure with operator training. The operator knows that they have to transfer a certain amount of acetone over every shift, and they're trained and they do it repeatedly, and that's our first safeguard. Next safeguard, maybe we have a high level alarm. So if the operator is distracted or whatever, and we reach a certain level in that tank, an alarm goes off, probably on the PLC, maybe a red light, and the operator is alerted, oh, okay, I forgot to turn off the valve, hits the button. If that fails, maybe we have another layer. We have a high level interlock. And here, if the operator is distracted, doesn't turn it off, and it reaches the high level, the system automatically shuts itself off. In other words, the transfer valve closes through some sort of a basic process control system. Typical for tanks like this, we also have secondary containment, which hopefully contains any spill into a designated area, so it can't really travel too far to find a source of ignition. And last but not least, we designed it as a Class 1 Div 1 or Class 1 Div 2, and so we have intrinsically safe equipment around this tank. So Sitting around the table, we all look at each other and we go, okay, based on these safeguards, what's the likelihood of having a overfilling situation leading to a fire? And everybody looks at each other and goes, well, that's pretty impossible. So I'm going to give it the lowest likelihood. I'm going to give it a 1. And so your overall risk score is 4 times 1, which for most folks is acceptable. And so we just go on to the next deviation. That's typically how PHAs work, especially ones where people are very familiar with the process and you've been doing this for 20 years, and this is kind of how it works. Well, what LOPA does is LOPA takes a look at these safeguards, and rather than just qualitatively saying yay or nay, or yeah, I'm comfortable with that or not, it actually puts a number to it as to what likelihood there is of failure of these safeguards. How often will the operator miss closing the valve? How often will that high-level alarm fail? How often will that high-level interlock not work? What about secondary containment? And what if there was an error in PMs and all of a sudden a non-intrinsically safe piece of equipment got put into the vicinity of that tank? That's what LOPA does. LOPA takes those things that we qualitatively assess and actually puts some numbers to them, so you can come up with a semi-quantitative risk score. Now I'll talk about how that's all done. So as we talked about, the safeguards are all considered protection layers. And for LOPA, the key is the word independent. So we're going to talk about this a little bit in detail. Independent protection layers are just that. They have to be specific, independent, effective, and auditable. What do you mean by specific? Well, an IPL can detect and prevent or mitigate the consequence of a specified potentially hazardous event, such as a runaway reaction, loss containment, or explosion. It actually has to do what it's intended to do. So think of a closing of a valve, thinking of an interlock, think of a dike. Okay, these are all specific items used to control a release. The word that most people get hung up on with IPLs is independent. The IPL has to be independent of the initiating cause, and also the IPL is independent of the other protection layers associated with the identified potential hazardous event. So let's go back to our little example again. So our operator is watching the PLC and opening the valve, watching the transfer of the acetone into the tank, and at a certain point we'll turn it off. Now there's a high-level alarm in there. That high-level alarm automatically will trigger the operator's attention should a high level be reached. Now the question becomes, are those two independent protection layers? The answer may be no, because quite honestly, the operator is the same operator in both. So they're really not independent. Obviously, they're protection layers. One is based on an SOP and training, and the other is based on some sort of electronic readout of level. So those are independent. However, the actuating event of a person stopping the flow is still the same person having to hit that same button. So in an argument there, you would probably say that even though those two things are protection layers, they're not necessarily independent protection layers. And we'll talk more about this as we go on. The IPL has to be effective, has to, you have to know what it's going to do, and it has to do it when you want it to do it, and it has to be auditable. In other words, you can go in and test it. You can go in and look and say, okay, is this a high-level alarm? Can we calibrate it? Is it an interlock that we can test? Is it an SOP or an operator qualification that we can actually validate by talking to the operator and looking at the SOP? So those are all things of what an independent protection layer has to be in order to be acceptable for LOPA. So let's look at some typical independent protection layers. Like I said, standard operating procedures, pretty common. We have them all over the place. It's something that is accepted in pretty much all chemical industry. And again, it's administrative control. Next, we have basic process control systems, typical fills and pressures and that sort of thing. We have alarms with defined operator response, just like in our example. We have safety instrument systems. These are interlocks. These are pressure controls. These are other things where now we're getting a little more sophisticated, and that there's an active system in place that's kind of controlling our process outside of just the SOP and operator instruction. Then we get into passive things like pressure relief devices, blast walls and dikes, and finally to the layer of really mitigation, which is fire and gas systems and deluge systems, which unfortunately don't eliminate the deviation, but they definitely reduce the outcome of that deviation. In other words, this would be a deluge system that would put the fire out should that acetone leak out of that tank and catch fire, maybe there's a foam system in place that will detect that heat or that temperature and automatically trigger. But this is kind of the hierarchy, if you will, of controls. We'll talk about that a little bit later too, but starting with the basic process control system on up to a mitigation system to limit the damage. So let's start talking about components of the actual LOPA, okay? So we talked a little bit about independent protection layers. We're going to come back to that. But there's other aspects to LOPA that you have to consider, and we're going to talk about these things in a little more detail. The first one is the acceptable risk criteria, okay, or better known as the tolerable event likelihood. This is your risk tolerance. So as a company, you may have a risk tolerance that says that, look, we want to limit our risk to 1 in 1,000 events, or 1 in 100,000, or 1 in a million, you know, whatever that happens to be. But there's a certain risk tolerance that your company has, and that doesn't necessarily go across the board. It may be very process specific. It may be very site specific. But even when we do our qualitative assessments, in the back of our mind, we kind of know when something seems to be risk acceptable and when it doesn't. So when you're doing a LOPA, that has to be determined, because that is pretty much your baseline for when you determine whether or not you've reached your level of risk acceptance. You also have initiating event frequencies. These are how often things fail in the beginning. What's the initiating event? You have enabling conditions, conditional modifiers. We'll talk about those. We already talked a little bit about independent protection layers, but they factor into this. And then at the end, you end up with your mitigated risk, which essentially is a product of all of these things combined. And quite honestly, what you end up doing is comparing your mitigated risk to your acceptable risk criteria to see whether or not you've reached the acceptable risk level that you've set for yourself. So let's talk about acceptable risk criteria. It's summarize your safety goal. That's how we look at it. It's the probability of failure past which the risks of the failure scenario are considered by the LOPA team, company, or operations as acceptable. And like I said, it could be very much focused on a particular event, could be on an overall process, could be at the site level, could be at a corporate level. And there might be different risk criteria at each level, and also may be based on what the outcomes are. So it's not a set fixed number in all cases, but it definitely is something that needs to be determined before you go on with a LOPA, because you'll never know what's acceptable unless you kind of draw a line in the sand, and this is the line that gets drawn. For example, a typical tolerable event likelihood for a single fatality may be 1 in 10,000, and that is not atypical. And when we say 1 in 10,000, we mean 1 in 10,000 events, usually over a period of a year. Okay, or 1 in 10,000 events over a period of lifetime. It really doesn't matter. It's really what is your acceptable failure rate, if you will, for a particular incident. And a catastrophic failure scenario might be 1 in 100,000. And obviously, the next level up would be 1 in a million. So these are kind of the numbers that you as a company, you as an individual working over a process, kind of keep in the back of your mind. And this is what starts the LOPA process, is you have to kind of determine what is my acceptable risk criteria. Then you start going down the initiating event frequencies. What happens at the beginning? How often does something happen? Okay. So for example, the root cause of a hypothetical incident investigation, you know, it could be an actuated valve on a cooling line fails, or you have an operator error, or BPCS failure. Something happens that starts the deviation process. And for example, even in our little simple scenario, we talked about the operator opening and closing the valve. So if the operator fails, in that case, they open the valve, but they fail to close it, and the tank continues to fill, that would result in a overfilled tank. That's an operator error. That's the initiating event frequency. And the question becomes what is that frequency? Well, let's go back to our simple example. Say that we're filling that acetone tank, as I mentioned, every shift, and you're running 3 shifts a day. So that's 3 times a day that tank gets filled, probably by 3 separate operators, because you're also on a shift schedule. And so you have 3 times a day where that gets filled. If you run for a year, and we'll use simple math, say 333 days a year, now you have 3 times 333, you're at to 1,000 roughly events. So you have 1,000 events a year where you could overfill that tank. So now you're talking about, okay, what is our Initiating event frequency, is it 1 in 1,000? Yes, that's kind of what it is. Yeah, we would have 1 failure in 1,000. Maybe from your experience, you're finding that that initiating event frequency is much higher than that. Maybe you find that you have overfilled that tank and you have had a spill in the dike. On the other hand, maybe you've been running that process for 20 years and the operators have never overfilled that tank. Those are kind of numbers, though, that you have to have in your back of your mind when you're doing this LOPA to figure out what is the typical initiating event frequency. But for simple purposes, let's say it's 1,000 times a year. So, one failure in 1,000 would be 1 in 1,000. Then you have some enabling conditions. These are kind of modifiers, if you will, that occur that may or may not add to the probability of a loss. So, for example, the state of operation is only risky during the cooking phase. Where we see this a lot is seasonal risk. Say you have an issue where your failures are mostly factored in with high water levels, and so you're really only focused on this failure rate when during the rainy season, for example, or maybe it's during hurricane season. Maybe another scenario where you're running a process where temperature is critical, and so if it gets too low, then that's a problem, and you're only really worried about that in January and February because that's the only time the temperatures really get that low. Those are enabling conditions. In other words, the event likelihood isn't the same every single time because there's some enabling condition that comes along. This is an optional calculation in the LOPA, but you can see where there are certain scenarios where enabling conditions may have to be factored in because it's not the same frequency of loss for every time it could happen. Another one is conditional modifier. Again, another optional add to the LOPA. Really, it means that this has to come alongside the initiating event for the loss event to occur. And one of the ones that I think is probably the most likely is that many chemical plants are designed so that people aren't necessarily around the active area when the risk is highest. So, for example, if you are transferring that acetone and you're worried about a fire that could cause somebody to get burned, maybe you only transfer acetone when no one's around, or you've designed it so that the acetone transfer process is totally automated and there's no operator involvement, or the control room is far enough away that they would never be impacted by it. It's that kind of thing. And so you do get some credit for that. You get credit for a conditional modifier where you've designed your process such that it's remote, or there's no one and there's no interaction, or you have done other things that make it more inherently risk adverse than if you were just running it as a normal process. And so sometimes you do have these conditional modifiers that, some people would call those controls, safeguards, and they could be. But again, either way, you want to take credit for that because that is something that has reduced your risk. And then we get back to independent protection layers. All right, so like I said, the bulk of the LOPA involves the assessment and the validation of these IPLs. Okay, and just a reminder, they have to be specific, independent, effective, and auditable. And then we have to figure out, how reliable are they? And there's a phrase called probability of failure on demand, PFD, and it is a measure of the effectiveness of the safety function. It's usually expressed in the likelihood that the safety function does not work when it's required to. So in that box on the upper right, you'll see typically how this works. And these are all orders of magnitude. We really don't cut it any more fine than that. Again, this is semi-quantitative methodology. So we try to just go orders of magnitude. So you figure if it's going to be a 1 in 10 failure, that's a 1 in 100, 1 in 1,000, 1 in 10,000. You can see how it goes up. And what you find is that everything pretty much has a inherent likelihood to fail. Some are very rare. Some fail more often than you would think. But in the event that you're trying to do this LOPA, you have to figure out what that failure rate is. So, for example, interlocks. Okay, everybody usually relies and says, well, the interlock is pretty reliable, and you're right, it probably is. And so you probably have a reliability of, say, 1 in 10 to 1 in 1,000 failures every time it's tried to be used. Pressure relief devices. Most people think, hey, those are pretty foolproof. Well, they are for the most part, but they have a failure rate about 1 in 100. And then human interaction, unfortunately, is probably the highest rate of failure. But again, we tend to rely on people the most. And again, you have to figure that into your independent protection layer calculations. So when you're looking at IPLs and you're looking at these PFDs, what you're trying to figure out is exactly how much failure is tolerable and how the failure is all tied together. Because again, typically in our scenarios, we are using multiple layers, and not every layer is as reliable as the next layer. And we tend to go from, say, a least reliable to a most reliable level, but that's not always the path that's followed. And so what you do is in LOPA is to try to assess each layer to determine what those different protection factors are, what those independent protection layers are, and on each of those independent protection layers, try to figure out how likely it is to fail when it needs to work. And it may turn out that when you add all this together, it turns out to be quite reliable. On the other hand, sometimes it's not. And that's what the whole LOPA exercise is about, trying to figure out what that is and try not to just focus on our qualitative judgment of how reliable we think things are. If you're looking for sources of information on what those probability of failure to demand numbers are, there's a list of resources that you can turn to, because many of these have been gathered over years of service for many parts, many different things, and the industry pretty much has a good feel for what the average loss rates are for certain things. So interlocks and valving and piping and vessels all can be calculated, or at least some data can be obtained that may apply to your industry. Now, the problem is that not all industries behave the same. Certain industries handling certain materials are going to have failure rates different than other industries handling different materials. And so it's hard to generalize sometimes, but that's part of this exercise with LOPA, is trying to make sure that the failure rates that you're choosing are as pertinent to your industry as possible. And if you are relying a lot on control technology, it's not just the sensor, but it's the sensor, it's the electronics, and it's the actuator that you have to consider. And those things, you can find out what the reliability of those factors are by going to many of these resources, and they will have lists of them. Or you can go to the equipment manufacturer, and they may tell you what the failure rates of certain things are. But that's all part of this failure on demand kind of calculation that you need to do to figure out how valuable or how reliable your independent layer is. All right, at this point, I'm going to take another survey because we talked a little bit about the automated systems and trying to do a using process controls. So, do you have a process with chronic process control issues? In other words, one where you're not relying on humans so much, but you're relying on automated systems, and yet you're still not confident that those automated systems are controlling the process to what you would want it to be. So yeah, it's one of those situations where when we talk with engineering, when we talk with operators, there's a heavy reliance on basic process control system, BPCS. And sometimes, and at least in our estimation, sometimes there's an over-reliance on these things. Sometimes people feel if there's an interlock on a valve, that it'll never fail, and that is our safeguard. That is our, that's our gold standard, an interlock in a valve. But if you look at the various PFDs for various interlocks, you'll find that they do fail, and they fail probably at a higher frequency than most people would think. And so it's something you want to think about. And again, this is where LOPA comes in, and it kind of level sets people when, for years they've said, well, that interlock is, that will never fail. And so they find that it's an eye-opening experience when they realize that maybe some of the things they were guaranteeing their safety on weren't as surefire as they once thought. All right, so let's talk a little bit about now the human factor aspect of this. So human factors is IPLs. And again, this gets back to our reliance, if we have such, on people and the operator's ability to do the job correctly. And how likely is it that the operator is going to make a mistake? Well, unfortunately, of all the PFDs, operators tend to have the lowest reliability. And you can find this data from a lot of times from NASA, and Department of Energy, and the Nuclear Regulatory Commission all have sources of data on human operator failures. And you find out that the typical person will probably make a mistake about 1 out of every 10 opportunities. And that number is obviously debatable. And you may say, well, my operators aren't typical, they're much better than that, and that may be true. But when we do a LOPA, we usually take into account a failure rate of about 1 in 10 for an operator. So let's go back to our initial example. And that initial example was filling that acetone tank 1,000 times a year. And if you have a failure rate of 1 in 10, that means that 10 out of those 100 out of those 1,000 opportunities, that person's going to overfill that tank without other safeguards. In other words, they're going to miss their ability to shut off the valve at the right time. And that is not atypical. And so that is why, and even in our example, we say, well, we have a high level alarm, and that's another trigger. And that means the operator has to step in and do another event. And if that doesn't work, we have another automated system that takes the operator out of the picture, and that adds additional control. So just getting back to this is that you got to figure out that the human factor is something that you cannot overlook when it comes to these LOPAs. And if you have a process that you were relying on manual intervention as your key means of control, you have to really think about whether or not you are going to meet your risk criteria for your tolerable risk criteria for control of this process. If you have examples of 2 people who have to sign off on a process, and good examples, say like a lockout tagout or a hot work permit, you can actually get a 1 in 100 failure rate. You can actually improve your failure rate by 1 or more order of magnitude. And that is predominantly because now you have 2 separate people looking over the same thing and both having to agree at a certain point that this is okay. So if you have a lockout tagout where the operator locks and tags a valve, say, and then the supervisor comes through or a maintenance person comes through and puts their lock and tag on it after that, then that is maybe a 1 in 100 chance of failure, as opposed to 1 in 10 where you would only have 1 person locking something out. That's kind of how you got to think about human operator interactions. It is possible to get 1 in 1,000, but that is pretty rare. You'd have to really show that you have essentially 3 people independently looking at something in order to say that you have a 1 in 1,000 chance of failure there. But like I said, for typical operators, it's 1 in 10. Now, why is that? Well, if you look on the left, there's lots of reasons why operators make mistakes, and none of them are intentional. A lot of them are related to distractions, or it's too much work and not enough time. Sometimes with older processes, complacency. It could be a lot of different things, which all lead to higher probabilities of failure. Machines aren't as affected by these things as people are, so therefore they're not distracted. They don't fail as quickly. But the bottom line is that is something that you have to factor in when you're doing your LOPA, that people are not as reliable as you may think. So now we're going to get to the meat of the issue, which is the mitigated risk. This is where it all comes together. Sometimes it's called the mitigated event likelihood. This is where you take all your inputs, put it all together, and come out and see whether or not your mitigated event likelihood is going to meet your tolerable risk. So what you do is you take the initiating event, the probability of that, times the which is better known as the unmitigated event frequency, multiply it by all your IPLs, all your conditional modifiers, etc., and then you come out with an overall risk score. If your PFD, probability of failure in demand, equals 1, then there are no IPLs. So in other words, that failure is a certain. But for the most part, you're going to have some sort of reduction in your event likelihood based on all these factors. And then you're going to try and figure out whether or not that mitigated event likelihood matches what you think is your risk tolerance. So what you do is you take your risk, and the risk is equal to your mitigated event likelihood times the severity, and then you figure out whether or not that meets your criteria for what is considered the risk that is tolerable to you. And so again, if you go on the bottom here, you can see that if the risk remains high, say, MEL stays high, say a 1 or 1 in 10 chance, your likelihood with a high severe outcome, you're going to have a problem. It's more than likely you're going to have a release of some sort. Now, whether or not that becomes catastrophic or not, there may be other factors in that you can add in there. But for the most part, you were trying to figure out whether or not that's going to meet our likelihood or our acceptable level for what is tolerable. If your risk is less than the tolerable event likelihood, then you've met your goal. If your tolerable event likelihood, for example, is 1 in 10,000 or 1 in 100,000, and you add up all your risks and your modifiers and everything, and you multiply them all together and your IPLs, and you're below that, then you are within the risk tolerance that you've prescribed. So like I said, this is really just to validate some of the qualitative thinking that goes on during a PHA. And it's a way to essentially validate that the IPLs, the safeguards, if you will, that you have in place are going to work when you want them to work, and are going to reduce the risk of that catastrophic event to the point that the management and the process owners are going to be that risk level is acceptable to them. And this is really what this whole exercise is all about. Now, what if that risk is too high still? What if you come out with this exercise and you go, oh my goodness, we're still at a higher risk than what's tolerable? Then you got to really reconvene the PHA team and maybe go back and look for additional safeguards. Maybe you have to reevaluate the safeguards you have. Were you too critical? Were you not critical enough, et cetera? And reevaluate what's going on. And it may turn out that you need additional safeguards. What you find typically in these scenarios is that as you go through this, especially for processes where you rely a lot on human intervention to control the process, it's very difficult to get to 1 times 10 to the 4th or -4, 1 times 10 to the 4th, 1 times 10 to the 5th event likelihood kind of scenarios. It's very difficult to get 4 and 5 layers of protection that are independent when you have a lot of people involved in the process. What you find is that you may have to switch or modify your process from being very manually intensive to adding more automation, because automation does increase the independence of your IPLs and does reduce your risk. And so typically, if you find that you have an older process where you're relying a lot on manual intervention, you may find that you are not meeting your risk criteria and you have to add some automation in order to make it more risk tolerable. What is acceptable risk criteria? Well, like I said, it's determined by the process owner. Typical values, like I said, fatality of 1 in 10,000. So if you have the factor of 10 to the 4, or explosion, 1 in 100,000, 1 times 10 to the 5. These are kind of the typical values. Some companies have a very low risk tolerance, and they say we want to be 1 in a million. And again, that just means you have one additional order of magnitude of protection that you have to factor into your process in order to get it to that goal. And obviously, what you can see here is that it's nice to say we have an acceptable risk criteria to be 1 in a million, but it's another thing to actually pay for that. Obviously, every one of these layers of independent protection costs money. And for you to operate your process in such a way that you want to have a 1 in a million failure rate, that may be a very expensive proposition for all the deviations that could happen in that process. So that's where the trade-off typically occurs. It's not that people want to factor in some sort of explosion or fatality. Where it really is what's the economics of trying to make something fail-proof or foolproof. Now, there may be situations that you say, yeah, we have to go to 1 in a million because it is completely intolerable for us to have this kind of a loss. Maybe it's related to where your facility is located. Maybe it's related to how severe that outcome would be if you had that loss. But at the end of the day, that extra protection costs a lot of extra money, and that's something that has to be traded off. And this tool of LOPA can help do that a little bit. Can help give you an idea of what it's going to take to get to those different risk tolerance levels and how much money it might take to add that extra layer of protection. So the typical LOPA process steps, we'll just kind of review this. You identify your PHA consequences for LOPA analysis. Like I said, generally severe or major risks, something that's typically in the severity category, probably something that's very red. Or you have a residual risk that is unacceptable. You identify the incident scenario and the cause associated with each consequence. That's typical PHA. You identify the initiating event and estimate the frequency of that initiating event. You know, how many times can it fail? What is the likelihood of failure, and that kind of thing. Then you identify your IPLs, your safeguards for the event. You've got to determine whether or not they're independent or not. And for each of those, you got to kind of figure out what the probability of failure on demand is based on the available resources or experience. And like I said, there's a lot of resources out there, but your experience may be more valuable than even some of those resources, especially for some unique industries. There may be situations where you have been running a plant for 40 or 50 years, and so your experience with how much your equipment fails is going to be more valuable than looking it up in a handbook somewhere. But not everybody has that kind of experience, and so you have to use what you have, and sometimes you have to go to the general industry resources to figure out what those PFDs are. Then at the end, you calculate your MEL, which is essentially your initiating event times your modifiers times your IPL PFDs, and that'll give you essentially your mitigated risk level, the MEL. And then you got to figure out what that risk is from your table based on severity and compare it to your tolerable exposure, which is something you've determined from the beginning. And if the risk is acceptable, you're good. You don't have to go any further. If it's not acceptable, you might want to go back and say, wait, we might have to add additional IPLs in here in order to bring this down to a level that we deem as an acceptable risk. The 4 primary benefits of using LOPA or safety integrated levels. 1, LOPA often reveals process safety issues not identified in previous qualitative risk reduction methods. And if anything else, this is probably one of the most valuable portion of this. If you're going to do a PHA, and it's a PHA revalidation for a process that you've been running for a long time, a LOPA may be something that will add some additional insight into maybe some assumptions you've made early on that no one's ever challenged and that you may not be fully comfortable with. So a LOPA can actually go in and say, hey, you know, we've been relying on these 4 controls for this process for 20 years. How reliable are they? Or it may turn out that you are having reliability issues and you want to look at some alternatives. What might be a more reliable alternative to having just strictly operator intervention when the lights and bells go off? So that's really where LOPA comes in handy. Process hazards are directly connected to the safety actions that must take place, providing clear identification of the safety instrument and systems and associated risk reduction. LOPA is effective in resolving disagreements coming out of qualitative hazard analysis findings. We've been in some PHAs where there's a large disagreement between what engineering thinks is an acceptable PFD and what an operator or management thinks is an acceptable PFD. And so, you know, let's go investigate it. Let's go look at what that PFD is. And a lot of times it's somebody's assumptions that said that this thing is very reliable, and yet somebody else comes back and says, no, it's not. It breaks all the time. And this way you actually have some data behind it to say, okay, what is the real failure rates? Whether it's based on your experience or maybe it's something you've heard in industry in general. And it may help you out with trying to figure out exactly what is the right control and independent control you want to put in place. And then LOPA can identify acceptable alternatives to the safety instrument and systems, such as adding layers of protection, process modification, or changing procedures, and allows the risk analysis team to evaluate potential risk reduction options using cost-benefit analysis. Like I said, the more controls you add, the more cost you add to your system. And so there is a cost-benefit analysis that should be completed. This is not an obvious thing, you know, and obviously there's going to be some disagreement over what is acceptable, and possibly a LOPA can help drive the discussion there over what is the benefit of, say, adding an integrated system or as some sort of interlock to your system, and what's the cost of that versus the potential loss. So that's all something that you may want to think about. We're going to add another question here. Are there steps in your process where you feel that you rely on operator expertise more than engineering controls? Again, the older the process, we find is the more likely operators are relied upon as opposed to engineering controls. But this is something that, again, is a LOPA can help uncover, and also a LOPA can help convince management that maybe investment in automation is better than retraining operators or something along those lines. So yes, thank you for your inputs. Looks like a lot of people felt that there are steps in your process where you rely on operator expertise more than engineering controls. And so that is not unlikely. And again, a lot of times this is a direct correlation to how old that process is. Newer processes tend to have more automation, maybe not as much operator intervention, but definitely older, more mature processes, because they work. People don't like to mess with them, and so they tend to be kind of sometimes heavy operator focused. But a LOPA may help with talking about that and verifying whether or not that's acceptable to folks. All right, let me jump in and finish up here. The next slide we're going to talk about is something that's familiar to everybody here, and that's your hierarchy of controls. And as we've mentioned already, you know, administrative controls like SOPs and training versus engineering controls versus isolation versus substitution, etc. We all know the effectiveness of these controls going up. And again, this is a very qualitative way to look at things. But at the end of the day, LOPA helps you put a little quantification to some of these layers. What is the value of an engineering control in terms of its independence and its probability for failure on demand as opposed to an SOP and operator intervention? What is the benefit to having a process that is designed with no operator intervention at all, and everything's done remotely, you know, and can we get credit for that we may not be taking advantage of? Those sorts of things. Those are the kind of decisions that LOPA can help you with, because it can actually put some numbers to it. So it's not just your judgment, your opinion, but you can actually see the value and can compare different control technologies one against the other and how effective they are. So just a reminder, LOPA is not a regulatory exercise. So this is something that's above and beyond. Unless it's a corrective action required by OSHA or corrective action required on your process, quite honestly, there's no external requirement for you to do a LOPA. It's really recommended as the best practice. So we try to encourage our clients to add this to their PHAs. So if you're going to do a PHA in a process, especially a revalidation, you can add this to a PHA for not a lot of extra money, because the actual LOPA itself, you're not doing every single deviation. You're trying to pick out, as we said before, maybe 5% of the deviations that may be most troublesome, or ones that have high residual risk, or the ones that have the most severe outcome. And you do a LOPA on those. And so the additional cost to a PHA is relatively minimal, but it really, I think, adds a lot of extra value to your PHA team, so they can kind of figure out what's going on. And like I said, any mitigated risk standing above the acceptable risk criteria can be evaluated, and maybe additional controls put in place. And then those additional controls, the PFDs, can be determined to see if they are that much more effective, or are you just adding another layer in there that may not be as independent or as specific as you thought it might be. Let me go in summary here. So LOPA summary, order of magnitudes. It's semi-quantitative approach to risk assessment. As you can see, it's more precise than a qualitative assessment, but we're not measuring it with a micrometer here. We're talking about orders of magnitude of protection. And so therefore it's not that precise. It's not going into safety systems per se, but it is giving you a little bit more quantification than your typical qualitative. It's a great cost-effective method for a deeper understanding of the process. Like I said, you can add this to a PHA for a few additional dollars, but it'll give you a much more robust outcome of your PHA. And it's a great plan for going forward based on mitigated risk. It's a good way to say, okay, we're doing everything we possibly can to reduce the risk of this hazard or the risk of this process. And we have a lot more confidence based on doing a LOPA that the controls we've selected are actually going to work when we want them to work, and that the process is going to be protected.
We'd just like to thank everyone again for joining us today. And just a reminder that all of these webinars are being recorded and will be viewable on the EnSafe website. It usually takes, a couple days to a week to get them posted sometimes, but keep checking back to ensafe.com, and you can view those later on. And I hope you will tune in next week for our webinar on the emerging contaminant PFAS, hosted by Adam Wiseman. So thanks again for joining us, and great job, Frank. This concludes our presentation.